My understanding of the biomechanical principles underpinning a squat is that it's just like anything else. There is no one way to squat, and everyone will have a different opinion on the biomechanics of it. There is also specific biomechanics that will work for you and only you, as everyone is different and we are our own individuals. A barbell squat is a multi-joint exercise that will develop the largest and most powerful muscles of the body and have biomechanical and neuromuscular similarities to athletic movements, such as running and jumping. Range of motion, or in this case the squat depth, can be represented as the ideal range of motion is to go parallel with the movement on the down phase of the squat. The feet positioning is a vital part of the squat, with the ideal position being about shoulder width and distance. Another piece of the puzzle when it comes to squatting is the bar positioning itself, whether it be a low bar squat or a high bar squat. The low bar squat coexists with the wider stance to adjust for the deeper lean caused by the low bar, whereas a high bar squat promotes different biomechanics in comparison to the low bar, as the bar positioning allows for a more upright position with the torso or the trunk. The high bar squat works with either closed feet or the ideal shoulder width stance. A squat is complex in nature due to the amount of muscles, tendons, ligaments, and joints that are involved in the overall movement. It is considered to be one of the most widely spread exercises for muscle sport training and is part of the competition movements comprised within the Olympic weightlifting. The center of gravity that must be maintained throughout the entire exercise as it changes due to the body position and the overall awkwardness and risk of injury in an untrained individual. The barbell squat is a large, compound weightlifting movement, and it is performed by placing the feet shoulder width apart and the barbell to be placed over the traps, which properly distributes the weight. The hands are to grip the bar within a supinated grip, while the hips are to be slightly thrusted forward and the abdominals pulled tight to create a slight arc within the lower back. The knees stay over the toes and the heels are kept in line with the barbell. As the descent begins, the chest is held high with the hips and buttocks moving downward until the angle of around 90 degrees is to be created. The thighs are kept parallel with the floor. The overall movement of the squat is kept within the transverse plane as the barbell moves within a straight line. These diagrams and videos shows the different forces during the squat as well as the path of the barbell and the body. The knees, toes, and upper chest are aligned with one another, and throughout the motion of the squat they remain within the alignment. The barbell stays in line with the soles of the feet to maintain movement along the force of gravity. Keeping this bar path and form is essential to get the most out of the exercise, as well as staying safe while performing it. The quality of sequential combinations of movements is dependent on the continuous flow of visual, somatosensory, and postural information that results in seemingly immediate integrated responsive actions. The movement of each joint and muscle in the squat changes on which phase of the squat is being performed. Within the diagrams and videos, you are able to see the force of the weight and the ground force reaction to be both in line with the center of gravity of the individual squatting. There are three phases of the barbell squat, which are as follows: the starting position, the descent, and the ascent, or the ascent. The major motion of the squat is based around the hip joint, knee joint, and ankle joint, and it is crucial to properly understand the effect of the application of movements or loads on the lower limbs of the body. The extension and flexion of these joints are made possible by muscles known as the prime movers. The hip joint is able to be extended due to the gluteus maximus, the semitendinosus, the semimembranosus, and the bicep femoris acting as the prime movers, whereas the knee joint is able to be extended due to the rectus femoris, vastus medialis, vastus intermedius, and the vastus lateralis working as its prime movers, whereas the prime movers that allow the ankle joint to be in plantar flexion are the gastrocnemius and the soleus. It is important to also note that during the squat, the pelvic girdle must be kept stabilized as it has the ability to move forwards, backwards, and side to side along several different axes. The semimembranosus, semitendinosus, the bicep femoris, and the gluteus maximus all have origins connecting into the pelvis itself. The pelvis must always be working to stabilize itself, which calls for recruitment of the spinal extension muscles and the abdominal muscles, which are able to provide a counterbalance force and keep the trunk steady. Joints used for force distribution in the position 1 are the hip joint, knee joint, ankle joint, and toes. The hips are anteriorly rotated and in slight flexion as it creates the overall squat position of the buttocks being pushed backwards and the upper body being forced forwards. This allows the weight to be vertically aligned within the center of mass and the center of gravity. The knee has a slight flexion as it is in a bent position of about 150 degrees. The ankle joint is held in its neutral position with the feet planted firmly on the floor. Progressing into the phase 2, the position of the joints and muscles begin to change throughout the beginning of the descent. During this phase, the hip joint is in flexion and the joints are all put under stress due to the descent phase of the squat. The hip joint is posteriorly rotated to balance the weight of the barbell. This is due to the fact that the lower the body moves, the lower the center of mass moves. To keep balanced, the weight must stay aligned with the center of mass and the center of gravity, thus keeping the movement on the same vertical axis as before. To be able to maintain this balance, the knees flex throughout the descent until it reaches about a 90-degree angle. Muscles in the lower extremity produce the power to be able to lift the weight back into the starting position. During the ascent phase, the body works to keep the squatter properly balanced. Lateral and medial rotation may occur as the glutes and hamstrings begin to contract to elevate the body. This results in the contraction of the hip joint muscles in order to neutralize the undesired rotation. As the knee joint extends, the quadriceps contract and create tension on the patella, and most knee injuries are due to muscular imbalance between the vastus lateralis and the vastus medialis. This imbalance causes an uneven force along the patellar tendon, making it susceptible to injury. Some speculate that muscle recruitment on the squat can be altered by a change of feet position, but this claim is false, as rotating the feet into different angles does not change the muscle groups active in a squat. This is proven in a study conducted by Boyden, Kingman, and Dyson, as they found the surface electromyographic activity of the vastus medialis, vastus lateralis, and rectus femoris on the right leg results in an analysis of variance indicated that the foot rotation positions did not influence the mean peak activity or mean duration of activity of any of these three muscles. The mechanics of the squat is greatly governed by the location of center of gravity throughout the exercise. Gravity aids in the descent portion of the squat as it helps the squatter to maintain balance throughout its descent. The center of gravity will change as it goes through the motion of the squat. As the squatter descends, the center of gravity is also lowered with them. One must keep the line of gravity straight and aligned with the line of support to maintain balance throughout the descent. This will help maintain balance and form throughout this whole phase of the squat. Overall, the barbell squat is one of the best exercises to perform by anyone. However, its ability to activate so many muscle groups come from its complexity of the exercise. The biomechanics of the squat require the mastery of the technique of squatting to prevent injury, but when mastered, the results can be phenomenal.
Good evening, and welcome to the biomechanics of the back squat. A very important biomechanical principle of the squat that is worth knowing is that the movement is entirely linear. This means that both the performer and the bar must follow set lines in order to reduce risk of injury and to ultimately gain the most out of each repetition. The lines within the body are known as moment arms. We have the knee moment arm and the hip moment arm. Blazevich described them as the perpendicular distance between the center rotation of an object and the line of action of the force acting on the object. Therefore, if we are to apply this to the activity in question, the object, by definition, would be the person squatting, and the force acting on them is the barbell. The athlete would consist of two moment arms as well as a straight and vertical line that the bar must travel along. The two moment arms, as I said previously, are the knee and the hip, and this line going through is the straight line that the barbell would follow. Seeing as though the hips are the main rotation force in the squat, it is crucial that the back remains straight to allow the majority, if not all, of the force to be placed upon the hips. We can see the line here of the back must remain entirely straight during the entire action. Then, during the action, the hip moment arm is then extended, and the moment arm of the knees is then shortened. This is due to the fact that during a squat, the performer's gluteal muscles do much more work than the quadriceps in terms of force production. So when the action is being performed, these muscles here produce much more of the effort than the quadriceps will. That is why the hip moment arm produces the most amount of force. It is also worth noting that a stable base of support is essential for a well-performed squat, for if the heels lift off the ground, it may displace the connection between the knee moment arm and the ground, thus reducing the amount of force produced overall. Done.
When sports scientists analyze athletes, they often investigate the different forces that are produced during movement. Torque is one of the different parameters that are studied. So torque is a force that causes rotation around a joint. So to figure out torque, you would need to figure out the length of the moment arm multiplied by the angle and then multiplied by the force, which in the case of the squat is gravitational force. So with an athlete squatting around 102 kilograms at the parallel position of the squat, we can freeze frame the moment, and it looks something like this. So the knee ends up at an angle of 125 degrees, the angle of the hip is 55 degrees, and the back angle would also be 55 degrees. Since there is parallel thigh position to the floor, the hip and back angle will be the same. So the knee moment arm, let's say in this squat, is 0.19 meters, and the hip moment arm, that is 0.27 meters. The moment arm length is a perpendicular distance from the joint to the vertical line of gravity that runs through the middle of the leg, which is a dotted yellow line. This means the overall thigh length is 0.46 meters, which is the hip lever arm and knee lever arm combined. This back will be represented as the connection to the spine to the pelvis. Now, when we multiply the weight, 102 kilograms by gravity, which is 9.81, which is equal to 1000.62 newtons of force. So this torque acting upon the knee joint at 125 degrees is 0.19 meters multiplied by 1000.62 newtons of force, which equals 190.1 newton meters. So then the torque acting upon the hip joint and the back at 55 degrees are 0.27 meters multiplied by 1000.62 newtons of force, which equals 270.16 newton meters. So through this diagram on the screen, we can see that through the weight of the bar, the gravitational pull and moment arm length, and how torque is created around the joints. The three National Strength and Conditioning Association performed a study in 2013 on torque in the knee joints during two variations of squats. One squat, the knees were freely allowed to move past their toes, lengthening their moment arm, and increasing the torque on their knee joint. The other variation was where there was a bar permitting the knees from going over the toes, which would keep their knee moment arm short and lengthen their hip moment arm. It was found that although restricting forward movement of the knees may minimize stress on the knees, it is likely that forces are inappropriately transferred to the hip and low back region. This means when performing a squat, it is important not to put too much torque on the hip moment arm, but also not to reserve or do the reverse and put too much torque on the knee moment arm for the sake of injury. Another major issue that is seen in the performance of the squat is the participant does not go low enough in the squat where their hips are slightly below their knees. This could be for a couple of reasons, such as lack of mobility. So due to an individual's differences in shape, size, and overall fitness, people inherently display differences in joint mobility, joint stability, and neuromuscular control. As such, a generic statement regarding squat depth for all individuals is inappropriate at best. Individuals who display ample mobility and joint range of motion combined with optimal joint stability may be able to safely perform squats using a full or near full range of motion. And this typically requires at least 15 to 20 degrees of ankle dorsiflexion and 120 degrees of hip flexion. If an individual possesses less than adequate ankle dorsiflexion, they may be at greater risk of injury to the knees, hips, or low back during functional movement patterns. In other words, each joint must exhibit proper range of motion for the efficient transference of forces throughout the body to produce ideal movement. A lack of technique is also another possibility, which could be incorrect feet placement, awkward bar placement, or even their chest being too low, which causes their back and hips to rise. Lastly, could be lack of stability, which could be that they're still learning the technique or unsure how to move their body, or it could even be the feet placed in an awkward position for the performer. An electromyographic study was undertaken by the National Strength and Conditioning Association in 2002, and the purpose of the study was to measure the relative contributions of 4 hip and thigh muscles while performing squats at 3 depths. EMG surface electrodes were placed on the vastus medialis, the vastus lateralis, the bicep femoris, and the gluteus maximus. EMG data were quantified by integration, and expressed as a percentage of the total electricity activity of the 4 muscles. It was found that the relative contribution of the gluteus maximus during the concentric phases among the partial were negative 16.9%. During the parallel squat, it was 28%, and during the full depth, it was 35.4%. The results suggest that the gluteus maximus, rather than the bicep femoris, the vastus medialis, the vastus lateralis, become more active in concentric contraction as the squat depth increases. By the performer of the squat going partially down, or even the hips parallel to the knee, they are missing out on activating their gluteus maximus and not achieving the full range of motion that is required by a squat. To achieve the full range of motion and activation of the gluteus maximus, a constraint is needed to correct their technique. The performer will start with a low weight bar in a seated position on the bench, placing their feet vertically under the weight and beginning to stand up. The performer will reach the top or starting position of a regular squat. They will return to a seated position while maintaining squat composure. Although this doesn't specifically activate the gluteus maximus through the exercise, it provides a prerequisite for quintessential squat depth. Once this constraint will be removed, we will be able to see if the constraint was successful by watching if they go to the depth of the bench when squatting without it. This would mean that they are activating the gluteus maximus and using a full range of motion for the squat exercise.
Analyzing one of our group members, we can break up the squat into its 3 phases, and it is possible for us to see that the performer demonstrating phase 1 has strengths in regard to their feet position, bar placement, and hand placement, which should all technically line up with the recommended technique that follows the center of mass and center of gravity lines. Now, as the descent begins, it is possible to see that the performer's chest begins to drop, as well as his head position is looking downwards, whereas his hips movements, his knee movements, and his ankle movements appear to be strong and require minimal adjustments. The ascent phase of the squat shows a good generation of force with a strong and stable base of support. When looking at the movement line of the barbell, it is possible to see that the bar is nearly going straight up and down, except for when he is at the base of his descent phase, prior to beginning of his ascent phase. This is believed to be due to the weakness demonstrated from the head looking down and the chest dropping out of alignment. The depth or range of motion of the squat appears strong and meets the full movement of the exercise, which can guarantee the most muscle involvement from the body's prime movers. Applying the constraints-led approach to this exercise, we aim to fix the demonstrated issue at hand. It is important to note that the goal of any exercise training program should be designed with the aim to improve the overall efficiency of human movement patterns. Whether the training program is designed to improve athletic performance, to rehabilitate an injury, or to simply improve overall physical fitness, the goal of performing repeated movements or exercises should be to make movement patterns more efficient. Now, as mentioned before, the leading issue appears to be a dropping of the chest and the head in the base descent phase of the squat. This tendency to look downwards is the first problem we are going to look at when we apply the following 2-step constraint-led process. The desired outcome and focus of this first constraint is to force the performer to keep their head positioning up throughout all phases of the squat. Even though it is mostly only seen in his descent phase, it is important to apply this practice throughout the whole movement and not just in the one segment. This constraint takes advantage of placing an object higher up and in front of the performer. The only direction to be given is to stare at the object and do not take your eyes off of it. The expected outcome that we want to see is that the performer's head positioning remains upright throughout the whole squat, which will ultimately promote a more upright torso and better alignment throughout the center of mass and center of gravity lines. Moving into the second constraint, we introduce a bench or a chair if you don't have a bench underneath the performer, and this will be used to focus and look at the range of motion and the drooping of the chest at the base of the descent phase. This rotation of the chest causes its center of gravity to ultimately shift and add an unwanted amount of stress and pressure onto the performer's upper spine, causing the exercise to become risky for any untrained individual and become a lot more harder for those who do know what they're doing. The idea behind introducing the bench was to promote a deeper range of motion while practicing a more upright chest placement. The performer is restricted by the bench, which ultimately stops them from going too low, which was one of the reasons why it caused the chest to droop. The expected outcome after the application of this constraint should show that the performer maintains a more upright torso position throughout the base of his descent phase due to the restriction. This constraint can ultimately coexist with our first constraint, as both constraints are able to be combined where the object and the bench can be vitalized at the same time, but only when the performer is ready for this step after working on the constraints at an individual level. As both the videos demonstrate, it is clearly possible for us to see that the desired outcome starts to occur when we look at the difference between the base descent phase of all the techniques that we have seen throughout this video. It is clearly visible that due to the applied constraints, we can see a decrease in the head and chest dropping with a higher promotion of the dorsal alignment in regard to the center of mass and center of gravity.